now discuss the modifications that Niels Bohr applied to the model of the atom so that the atom model could explain familiar phenomenon. Now, Niels Bohr was familiar with the emission spectrum of hydrogen. Now, there are new terms for you, is that right? What is the meaning of emission spectrum of hydrogen? Well, you see, every element can be made to emit characteristic light. Now, the light that I showed you some time ago, you see, I showed you this tube. This is actually filled with hydrogen. And the light you see here, I turn it on and you see the light it produces. This is the light produced by hydrogen. Now, what is the meaning of emission spectrum? Now, look at the hydrogen light. If I can pass this light through a prism, I can now obtain the spectrum of this. Now, what is the meaning of spectrum? You know that each color, every color, or any light is actually made up of colors. So, if I can pass this light through a prism, I can actually break it into colors. And I can get the spectrum of that. Alright? Do you want to look at the spectrum? Well, I can try. There is a limit to what I can do on the camera. So I'm going to see if I can show you how the spectrum of this will look. Okay. What you're watching now is the light emitted by hydrogen, and I'm going to let this light pass through a sophisticated equipment called a spectrometer, and I will see if I can show you the spectrum of this light. There are three distinct colors that are emitted by hydrogen, and one is blue that you're seeing now. And if you see later, I have to keep moving the camera to catch it. Now, this is violet. So look at these two, blue and violet. The other prominent one is actually red. I don't know if I can actually catch it, but have a look at the blue and violet. All right, there you got violet or purple. I will see if I can show you the red. Well, I have been able to get red as well. This is red. So how many colors did we see now for hydrogen? There are three colors: red, blue, and purple. Well, unfortunately, you cannot see all of these colors together in the camera. So I'm going to now turn it off. You have seen the three colors given off by the light emitted by hydrogen. Now, Bohr was familiar with this phenomenon. What phenomenon that we talked about? When light produced by hydrogen source is passed through a glass prism, it splits into discrete colors. Well, let me actually show you the equipment that I used to do this. Now, here is the equipment that I used. This is a very sophisticated equipment. Now, this is called a spectrometer, and I used what is called a grating, not a prism, to produce the spectrum. All right. And when you watched it, it was not very spectacular. But I just wanted to show you that when light emitted by hydrogen is passed through a prism or a grating, you can see those discrete colors. Now, this is what happens. This is the light coming from the hydrogen source. When it passes through a prism, each color deviates slightly differently. So you get red, blue, and purple. the way you see here. Each color in the spectrum corresponds to a particular energy of radiation. You know that by now. A red color corresponds to a lower energy, and purple corresponds to a very higher energy. And that's the reason why they split, because each energy will deviate slightly differently. Just like if two cyclists are going on the road, one is going slow, the other is fast, the fast one will deviate more than the slow one. Is that right? Yes. So the purple color, which is more energetic, deviates more than red, which is low energy. That means it splits into its constituent colors. And look at the colors that we saw in the spectrum. We have a red, well, blue and purple. The purple is not very clear here, but you actually saw that purple in there. Now, since these radiations come from atoms of hydrogen, you see, these radiations, red, that is low energy, blue, that is a little higher, purple, which is a little more higher, each of these different energy radiations come from the atoms of hydrogen. Then the structure of the atom must have something to do with it. Therefore, we must be able to modify the structure of the atom based on this. And that is what Niels Bohr did. So Bohr argued that atom can only emit radiations of certain frequencies. You see, the hydrogen atom only emits certain frequencies. It doesn't emit all frequencies. Does it? No. In fact, it doesn't give out white light. The light that is given up by hydrogen has only discrete frequencies. That means an atom can only emit discrete frequencies. One frequency corresponding to red, a second frequency corresponding to blue, a third frequency corresponding to purple. These are the only frequencies that a hydrogen source can emit. Now, he connected this to the model of the atom because an electron in an orbit is in a particular state of energy. Now, we have talked about potential energy, and if you remember, we said energy of two objects are minimum when they are closer together. Do you remember that? If you want to move them away, the potential energy increases. So, as the electron moves away from the nucleus, it has to have a greater energy. So, an electron staying in an orbit close to the nucleus has a low energy. An electron staying in an orbit away from, a little more away from the nucleus has a higher energy. As an electron moves away from the nucleus, its energy also increases. So an electron in an orbit corresponds to a particular energy value, and that leads us to the Bohr model of the atom. What is the Bohr model of the atom? Bohr came up with 4 postulates. What are postulates? Well, they are like hypotheses, suggestions, or arguments. Now, the first postulate says electrons assume only certain orbits around the nucleus. You see, an electron cannot be anywhere it likes. It can only assume certain orbits that correspond to a particular energy value. And those orbits are called stable orbits or allowed orbits. And Bohr said as long as these electrons are in their allowed orbits, they will not radiate energy, and they will not lose energy, and they will not collapse into the nucleus. You see? and only certain orbits are allowed. Not all orbits are allowed. That means you have the nucleus here. There are only certain orbits allowed. Now this is the first allowed orbit, and that corresponds to a particular energy value. If you want to call that energy E1, let's call that E1. Alright? If the energy of an electron there's an electron there, its energy will be E1. Alright? And so on. That means if an electron has to stay in an allowed orbit outside here, its energy has to be greater. An electron in an outer orbit has to have a greater energy. So this electron has an energy E2, and if an electron has to be still outer, its energy will be E3. So each allowed orbit has a specific energy value associated with it, and that is the essence of this first postulate. Now, what does the second postulate say? The second postulate says each orbit has an energy associated with it. For example, the orbit closer to the nucleus has an energy E1, the next closest has an energy E2, and the next one has an energy E3, and so on, and only these orbits are allowed. Electrons cannot be anywhere else. And the third postulate said, very important one, light emitted. When is light gets emitted? Remember, light is energy. When will an atom emit light? Light gets emitted when an electron in an outer orbit. Now, remember the energy level there. Let me write that one more time. An electron here has an energy E1. An electron there has an energy E2. An electron here has an energy E3. Now, when is light emitted? Now, Bohr has a very clever theory. He said, if an electron from this outer orbit that corresponds to energy E2 move to an inner orbit, well, the only way it can do is to throw away the extra energy. And it is that energy that is thrown away that comes out as light. Light is emitted when an electron jumps from a higher orbit to a lower orbit. And light gets absorbed when electron jumps from a lower orbit to a higher orbit. That means atoms can absorb energy. Now, very often when you heat an atom, it absorbs energy. When an atom absorbs energy, what happens? Electrons from the inner orbits will jump to the outer orbit. Now, an electron that has jumped like that will not stay there for long. It will want to come back. And when you want to come back, when it goes from orbit 2 to orbit 1, it has to emit the extra energy. The energy E2 minus E1 is emitted. Now, when it goes from the third orbit to the first orbit, it throws away E3 minus E1. Look at that. The energy E3 minus E1 is greater than the energy E2 minus E1. So, if E2 minus E1 gives off a red photon, then E3 minus E1 will give a blue photon. You see, different photons corresponding to different energy. All right. What is the next postulate according to Bohr? The fourth postulate said the energy and the frequency of light emitted or absorbed is given by the difference between the two orbit energies. An electron jumping from the second orbit to the first orbit will emit the difference between those two energy levels. An electron jumping from the third orbit to the first orbit will emit the difference between those two energies. That is what postulate 4 says. The energy and frequency. Remember, the frequency is determined by the energy. A higher frequency radiation is a high energy radiation. Is that right? Now, purple or violet is a high frequency radiation. Red is a low frequency radiation. The energy and frequency of light emitted or absorbed is given by the difference between the two orbital energies. Alright. The allowed orbits are characterized by the energy of the electron in that orbit. So these are the allowed orbits. And these orbits are characterized by the energy the electron will have in that orbit. Is that right? And these orbits are labeled n equal to 1, n equal to 2, n equal to 3, and so on. So the inner orbit we name n equal to 1. The second orbit is n equal to 2. The third is n equal to 3, and so on. Well, n equal to 1 corresponds to an energy E1. N equal to 2 corresponds to an energy E2. N equal to 3 corresponds to an energy E3, and so on. N equal to 1 corresponds to the lowest energy, E1. And that energy state is called the ground state. An electron in the orbit n equal to 1 is called the electron in the ground state. And remember, Bohr model only talks about hydrogen atom. And how many electrons are there for hydrogen? Just one electron. And normally that electron is in the ground state. Alright? What is the ground state? Ground state is the inner orbit n equal to 1, and the energy of the electron in that orbit is E1. If an electron receives specific amount of extra energy, so for hydrogen, remember there is only one electron, and that electron normally, in the normal case, is in the ground state, n equal to 1. If you heat hydrogen, now what I did in here, of course the hydrogen is inside, what I did in here is to pass electric current through it. You see, passing of electric current gives extra energy to these hydrogen atoms. Now when you give extra energy by way of heating or using electricity, what happens is an electron in its ground state can jump to the next state, n equal to 2, or n equal to 3, n equal to 4, and so on. And such an atom where the electron has jumped from the inner orbit to one of the outer orbits is called an excited atom. So when energy is supplied, external energy is supplied, an electron can jump to a higher energy level corresponding to n equal to 2, n equal to 3, and so on, corresponding to energies E2, E3, and so on. And the electron is then said to be excited. That electron is excited. It is no longer normal. Now, we know when people get excited, do they stay in the excited state for a long time? No. They have to come back to the ground state. In the same way, an electron that is excited will not stay in the excited state for long. It will come back to the normal state. So from the outer orbit, it will jump into one of the inner orbits. An electron cannot stay in the excited state for long. it returns to one of the lower levels by throwing away energy. And this thrown away energy is what we see as light of different colors. Why different colors? Because of the difference in the energy. You see, if an electron from the third orbit goes into the second orbit, it will emit that energy difference. That will be a very small energy, a red photon, for example. Okay, now this is what happens. This electron just came from an outer orbit. It jumped from an outer orbit to an inner orbit, and it is throwing away that extra energy. And this is what we see as light. So light is actually emitted by electrons when they move from an outer orbit of high energy to an inner orbit of low energy. It throws away the extra energy. Now here I have a picture of that. Now this is n equal to 1, this is n equal to 2, this is n equal to 3, n equal to 4, n equal to 5, and so on. Now, an electron in the excited state n equal to 3, if an electron is here, in this state of n equal to 3, it has an energy E3. If this electron now jumps to n equal to 2, now watch this. An electron at the excited level n equal to 3 jumps to n equal to 2, it gives off that difference in the energy. How much? E3 minus E2. And do you remember in the last lesson I told you the energy of a photon? Now this is a photon now. You see, light is made up of energy packets called photons. What is the energy of a photon? I told you in the last class is h times the frequency of the photon. So that energy is E3 minus E2. E3 is the energy of the third level. E2 is the energy of the second level. So an electron jumping from n equal to 3 to n equal to 2 will emit that extra energy E3 minus E2. And this bundle of energy is what we call the red photon, and its frequency is HF red, where F red stands for the frequency of red. You see, that is how you get the red color. Red color is emitted by an electron that jumps from n equal to 3 to n equal to 2. Isn't that beautiful? There you are. In the same way, an electron jumping from n equal to 4 to n equal to 2 will emit the energy E4 minus E2. And that is a green photon. So there you have a green photon. There you are. An electron jumping from n equal to 5 to n equal to 2 emits the energy difference E5 minus E2, and that is a blue photon. You see, when the energy difference is bigger, you get a higher energy photons. The red photon carries the least energy. The green photon carries a little more energy. The blue photon carries much more energy. So this is the mechanism of light emission. Now look at the way Bohr has been able to codify or modify the atom to explain and observe the phenomenon. This is how scientific theories originate. Okay, there we are. Now, radiations emitted by electron transitions. What is electron transitions? Electrons moving from one level to another. Radiations emitted by electron transitions from higher excited state to the first excited state. Now, if you look at these levels, the first level is called n equal to 1, the ground state. The second level, n equal to 2, is called the first excited state. For hydrogen, there's only one electron, and that is normally in the ground state. You see, when it receives extra energy, it goes to the first excited state. If it receives more energy, it goes to n equal to 3, the second excited state. And now, what we saw here is electron transitions from higher energy states to the first excited state. Now, this series of radiation is called Bohr series. In fact, visible light, the light that we get from the sun, the visible light is produced by atoms due to these transitions. Electron transitions from outer energy levels to n equal to 2, the first excited state. And that is what gives the visible light. And that series is called Bohr series. So this is the Bohr series, which is red, green, and blue. Alright. Bohr series correspond to the visible light. The light that makes us see things is the Bohr series of radiations. On the other hand, when electron transitions end on the ground state, if now the excited electrons jump back to the ground state from the outer orbit, the radiations given out will be much more energetic, and they are called the Lyman series, and they correspond to the ultraviolet radiations. So ultraviolet radiations are energy given out by electrons that jump from higher excited state to the ground state. The energy difference there is very, very significant. And that's the reason why ultraviolet radiations are very high energy radiations. Now, this is called the Lyman radiations. They are ultraviolet radiations. On the other hand, if electrons jump from outer excited state to n equal to 3 over here, that energy will be very small. When electron transitions end on the second excited orbital over here, electrons jumping from any of the outer orbits to n equal to 2 gives a third series of radiations called Paschen series, and that is the infrared radiations or heat radiations. So these three radiations you should be very familiar with. Ultraviolet, that's the Lyman series of radiation. Visible light, that is the Bohr series of radiations. And Paschen series, that is the infrared radiations. You can see infrared are very low energy, then comes visible light, and ultraviolet are very high energy radiations. There I have all those three series. The Lyman series, the very high energy radiations, are given out by electrons jumping from outer excited orbits to the ground state. The energy given off are very high. Visible light, called Bohr series, are produced by electrons jumping from outer orbits to n equal to 1, the first excited state. And the Paschen series, that is the infrared radiations, are emitted when electrons jump to n equal to 2, the second excited state. Alright, so that must be familiar. Very high energy. Visible light is the medium energy, and infrared are very low energy radiations. Now, Bohr series for hydrogen will look like this. Now, unfortunately, when I showed you this, I could not show you the whole spectrum. There you have the H alpha, they're called H alpha, hydrogen. See, alpha, beta, gamma, delta are the Greek equivalents of A, B, C, D. So H alpha is the hydrogen, the first line for hydrogen. H beta, H gamma, mostly what you saw are red, green and purple. These are the lines that I showed you in the beginning. Well, you could not see it well, but that's the best I could do using the equipment I have. So the energy difference between two levels, you see, when an electron jumps from one energy level to the next, the energy difference between two levels is called a quantum. And each photon has a quantum of energy. And that quantum can be of different value. You can have a bigger quantum, the ultraviolet. The quantums are different, how bigger, is that right? Okay. The energy levels specified by N1, N2, N3, etc. are called the principal quantum numbers. Now, let me draw an energy level diagram for you. This is the ground level, n equal to 1. And now remember, don't get frightened with these numbers. I'm just showing this to you for interest only. You don't need to learn all these values. The energy of an electron at the ground state is this value. I'm not even going to read it. I'm just going to write it down. So, the lowest energy level is the ground state. And that is the energy of an electron at the ground state. Now, the higher states are excited state. So, an electron on the ground state is given extra energy by way of heating or any other method. It can jump into any of the higher excited state. This is n equal to 1 or n equal to 2. And look at the energy value there. Alright, n equal to 3. This is the energy value. N equal to 4. This is the energy value. You can see if you look at these energy values are steadily increasing. They're all negative values. So they are steadily increasing. N equal to 5, that is the energy value. N equal to 6, I have given you now all the energy values all the way to the 6th excited state. Alright, an electron in a hydrogen atom will be normally on the ground state. Now, higher temperature, these are some of the reasons for electrons to jump to the excited state. What are the reasons? Higher temperature or electrical discharge. What I used to show you the spectrum is electrical discharge. So, higher energy or electrical discharge can give the electron sufficient energy to jump to the different excited state. Now, the energy of an electron in the ground state is negative 2.18 times 10 to the negative 18 joules. There we are. The energy of the electron in the first excited state is negative 5.14 times 10 to the negative 19 joules. And this is greater than this. Now, which of these two energy values is greater? Of course, as you go higher, the energy values are getting greater and greater and greater. Alright, let's now look at some of the electron transitions. An electron will not stay in a higher excited state for long. The electron jumps back to lower levels emitting a photon, and the energy of that photon will be the difference between the two energy levels. Now, the energy of a photon for a transition n equal to 3 to n equal to 2. Alright? Let's say an electron from n equal to 3 is going to move down to n equal to 2. what will be the amount of energy given out by that electron? It will be this value minus this value. Now, can you do that on a calculator? Well, as I told you, you don't really need to worry about it. But if you really want to do it, go ahead, give it a try. This value minus this value will be the energy of the photon that is emitted when an electron jumps from n equal to 3 to n equal to 2. I have calculated this and I got the value as 3.02 times 10 to the negative 19 joules. Now look at that. That is the energy of a red photon. The energy of a red photon as it jumps from n equal to 3 to n equal to 2. Now this is the energy of the red photon. Now find the energies of the green, blue and violet photon. You see, a transition from n equal to 4 to n equal to 2 will give you the green. You see, the green photon is emitted for this transition, n equal to 4 to n equal to 2. A blue photon is emitted when an electron jumps from n equal to 5 to n equal to 2. And the energy of this quantum or this photon is this value minus this value. I'm going to leave it for you to find out if you are interested. And a violet photon is when an electron jumps from the excited state n equal to 6 to n equal to 2. You see, what do you call this series of radiations? This series is called the Bohr series. That means electrons jumping from outer energy levels to n equal to 2. And that is visible light. You see, all the colors of light that we see in visible light is due to this transition. Well, obviously, the method or the model that we have talked about so far does not satisfactorily explain everything. You know why? The Bohr model ultimately needed revision. So Bohr model is not the model of the atom. It has problems. Now, what's the problem? It needed revision because Bohr model can only explain the behavior of hydrogen. It does not explain the behavior of higher elements. You see, if you look at the spectrum of oxygen or nitrogen or carbon dioxide and so on, they will be much more complicated. That means you need much more, intricacy in order to explain these phenomena. So Bohr's model ultimately needed revision because it failed to explain the nature of atoms more complicated than hydrogen. In 1921, Louis de Broglie introduced the wave-particle duality. We just talked about a bit in yesterday's class. Wave-particle duality. It means a particle behaves like a wave and a wave behaves like a particle. You see, it is Louis de Broglie who actually introduced that. You know, he was only 22 years old when he got his PhD in physics. And his PhD thesis was just one paragraph. One paragraph. And that is the particle-wave duality. Now, de Broglie suggested that particles could sometimes behave as waves, and waves could sometimes behave as particles. Particles have a momentum. You remember that. Momentum we represent by P, and waves have a wavelength lambda. These are the distinguishing characteristics. Particles have momentum, waves have wavelength. And de Broglie came up with a famous equation that earned him his PhD at that age of 22. And this is the equation. Wavelength equal to h over p. He said every particle including you and me, are waves with a wavelength given by lambda equal to h over p, where you remember that mysterious number I told you is h, is called Planck's constant. Don't worry about it. P is the momentum of the object. Now, classical physics have always assumed that precise location and velocity of the object was possible. Now, until this time, it was the understanding of physicists that you have an object, we can locate where exactly the object is and measure how fast it is moving. But when it comes to the principles suggested by de Broglie, now remember, all these principles become valid only when you think about particles like electrons, photons, very, very light particles. So you've got to go down to the subatomic level. According to Werner Heisenberg, it is impossible to have precise information about the location and velocity simultaneously of a particle such as the electron. You know why? If I want to look at something, now tell me, how am I able to look at something? Because light falls on it, light gets reflected from it, comes to my eye, I'm able to look at it. But if you want to look at an electron, when light falls on it, remember light is a photon. When a photon falls on it, it alters the position of the electron. So the fact that you have used the light to locate an electron has changed the position of the electron. So can you locate the position of an electron accurately ever? No, you cannot, because you can only locate it by using light. And when you allow light to fall on it, it's going to change the position of the electron. So you can never measure the exact position of the electron and its velocity simultaneously. Because if you do that, when you measure one precisely, you will alter the other. By measuring its velocity, you have changed its position. Right? Now, he suggested that the location of an electron around the nucleus is a probability function. So, Heisenberg said, unlike what Niels Bohr said an electron can exist in an allowed orbit and you can locate that electron there. But what does Heisenberg say? Well, you see, you cannot locate exactly where that electron is. So the concept of the allowed orbit is a fuzzy concept. There isn't a single orbit called allowed orbit where you can determine the position of the electron. You can only have a region where you have the probability of an electron being found. Now, Schrödinger introduced an equation that determines the probability that an electron can be located at a certain distance from the nucleus. You see, look at all the work that had been done in the early 20th century. All this is the development of quantum mechanics. And we are going to talk about all these in about 10 minutes. So the location of an electron is now specified by a name called orbital. Now, an orbital is not the same as the orbit. An orbital is different. What is an orbital? An orbital is actually a three-dimensional space where you have the maximum probability of locating the electron. It is no longer that good, neat orbit given by Niels Bohr. That doesn't exist anymore because of the Heisenberg uncertainty principle. An electron cannot be located in an exact position. You can only talk about the probability that the electron may be found in a given region. and that is given by the orbital. Now, each energy level is specified by the principal quantum numbers. I actually told you that before. And they are your N1, N2, N3 as Niels Bohr suggested. And each of these has subshells, S, P, D, F, and so on. So, Niels Bohr's orbit is no longer a single orbit. It is actually made up of many different types of subshells. The orbit that corresponds to n equal to 1, the energy level that corresponds to n equal to 1 has subshells. The energy level corresponding to n2 has also subshells, and the subshells are named S, P, D, F, and so on. Now, each subshell has one or more orbitals. Now, look at the intricacy, the complication now the quantum model is going to bring in. According to the quantum model, the orbit that is specified by Bohr at n equal to 1 is not a single orbit. It can contain subshells. We name them as S, P, D, F, and so on. And each subshell can contain one or more orbitals. An orbital is the space where the probability of finding the electron is specified. So each orbital can hold 2 electrons. Alright, take note of that, it's very important. Each orbital can hold 2 electrons. So here, each of these principal energy levels, E1, E2, E3, E4, and so on, are now made up of subshells. Here, this is an orbital, the picture of an orbital. Look at this. An orbital is a three-dimensional space where the probability of finding an electron is maximum. An electron distribution sketch representing a three-dimensional space around the nucleus where there is greatest probability of finding an electron is called an orbital. So this is the orbital of the S shell, and this is an orbital of a P shell, and this is an orbital of a D shell. Remember, each of these subshells, S, P, D, and so on, can have different orbitals. And how many electrons can there be in an orbital? An orbital can have 2 electrons. Well, we will now use this concept to build what is called electron configuration. Now, what is the meaning of electron configuration? How are actually the electrons distributed around the nucleus? That is what we call electron configuration. Now, we use the lowercase o. Well, there can be many representations, but this red O will be now used to represent an orbital. Each orbital can hold 2 electrons. That means n equal to 1. N equal to 1 has the S subshell. It has 1 orbital. So how many electrons can there be at n equal to 1? An orbital can hold 2 electrons. So n equal to 1, there is 1 orbital for the S subshell. The S subshell therefore can hold 2 electrons. You see, n equal to 1 has only 1 subshell, and that is the S subshell. And this S subshell has 1 orbital, and that orbital can hold 2 electrons. There you are. Energy level E1 has 1 subshell, and that can hold 2 electrons. Let's now talk about n equal to 2. N equal to 2 has the S subshell, well, and also the P subshell. So the energy level n equal to 2 can have two subshells. What are they? S and P. Now, there are 3 orbitals for the P subshells. Now, how many orbitals for the S subshells? 1 orbital. Now, that means P subshells can hold 6 electrons. So, there can be 6 electrons there in the P subshell, and the S subshell can hold 2 electrons. Therefore, how many electrons are possible in the energy level n equal to 2? There are 6 electrons in the P subshell, because P subshell has 3 orbitals, each orbital having 2 electrons. That is 3 times 2, 6. Plus there are 2 S electrons. There can be 8 electrons in the n equal to 2 energy level. The energy level corresponding to n equal to 1 can only have 1 subshell. And look at the way we represent it. 1s. Now what does 1s stands for? It stands for the S subshell for the first energy level. And the energy level corresponding to n2, n equal to 2, can have an S subshell and a P subshell. And we denote them by calling them 2s and 2p. What does 2s stands for? 2s means the S subshell of n equal to 2, n equal to 2 energy level. 2p means the P subshell for n equal to 2. Now, how many electrons can there be? Let's go back one more time. N equal to 1 can only have an S subshell. And an S subshell can only have 1 orbital. And remember, each orbital can have 2 electrons. Can have, it doesn't mean it has to have. 1 orbital can have 2 electrons. So, n equal to 1 can contain 2 electrons. The energy level n equal to 1, the ground state, can contain 2 electrons. N equal to 2. Now, S orbital can contain 2 electrons. And P shell, the P shell can have 3 orbitals. And each orbital has 2 electrons, giving a total of 6 electrons in the P shell and 2 electrons in the S shell. So the energy level n equal to 2 can have a total of 8 electrons. Alright, let's see what happens to n equal to 3. N equal to 3 can have an S shell. Look at the way we name it. We're going to name that S shell as 3s. 3s stands for the S subshell for n equal to 3. And it can have a P subshell. We call it 3p. The P subshell for n equal to 3. And it can have a D subshell. And a D subshell can have 5 orbitals. You see, I don't want to take you any further than that. It's going to get very complicated. Even now it is complicated. But try to understand as much as you can. Alright? Don't get frustrated. Alright? The S subshell can only have 1 orbital. P subshell can have 3 orbitals. D subshell can have 5 orbitals. And each orbital can have how many electrons? 2 electrons. Alright, now tell me, how many electrons can there be in the energy level n equal to 3? You can see there are 2 electrons in the S subshell. And how many electrons in the P subshells? 3 times 2, 6. And how many electrons in the D subshell? Each orbital can have 2 electrons. So 5 times 2, 10. What is the total number of electrons in the energy level corresponding to n equal to 3? There will be 10 plus 6 plus 2, 18 electrons. So there are 5 orbitals in the D subshell. The D subshell therefore can hold 10 electrons. The n equal to 3, that is energy level E3, can have 3s, 3p and 3d. Remember that 3 stands for n equal to 3. The S subshell for n equal to 3, P subshell for n equal to 3, D subshell for n equal to 3. Now we can summarize the electron distribution. We will leave the big picture to chemistry students. For us, we're going to just summarize this in a smaller picture. Main energy level, which we call n equal to 1, n equal to 2, n equal to 3. Then energy sub-levels. Each can have S, P, D, F and so on. And the maximum number of electrons and the maximum number of electrons per main level. Alright, let's go. N equal to 1 can only have the S subshell, and S subshell can have 2 orbitals, and each orbital can have 2 electrons. So the maximum number of electrons in the S shell is 2 electrons. And therefore, the maximum number of electrons in the energy level corresponding to n equal to 1 are 2 electrons. Alright, look at n equal to 2. The main energy level n equal to 2 can have subshells S and P. Now, S subshell can hold 2 electrons. P subshell can hold 6 electrons, 3 orbitals, 6 electrons. A total of 8 electrons are contained or can be accommodated at the main energy level n equal to 2. How about n equal to 3? N equal to 3 can have S, P and D subshells. S subshell can have a maximum of 2 electrons. P subshell can have a maximum of 6 electrons. And D subshell can have a maximum of 10 electrons. The total number of electrons in the main energy level corresponding to n equal to 3 will be 10 plus 6 plus 2, 18. Well, we can actually go on, but I don't think you want that. Now, I want you to look at the way we represent these electrons. Now, try and see if you can understand it. Now, what does 1s2 means? Each of these numbers has a significance. This 1 stands for the main energy level, n equal to 1. Now, the S subshell in the energy level n equal to 1 can hold 2 electrons. So 1s2 means 2 electrons in the S subshell corresponding to n equal to 1. Alright, let's now go to the next one. How are these 8 electrons distributed? These 8 electrons are distributed as 2s2. What does that mean? It means 2 electrons. Watch my aluminum pointer. You see how useful that is? This 2 says 2 electrons in the S subshell for n equal to 2. What does 2p6 tell you? 6 electrons in the P shell of n equal to 2. So, these 8 electrons are configured as 2s2 to p6. Alright, how is the electrons configured in n equal to 3? And look at the way they are written. 3s2, 3p6, 3d10. What does that mean? 2 electrons in the s subshell of n equal to 3. 6 electrons in the p subshell of n equal to 3. 10 electrons in the d subshell of n equal to 3. That's the meaning. And when you write electrons in that way, it is called the electron configuration. Now, hydrogen with 1 electron in the s subshell has what electron configuration? Can you tell me what is the electron configuration for hydrogen? It has 1 electron in the s subshell. Well, its electron configuration is 1s1. That is the configuration for hydrogen. In other words, 1 electron in the s subshell of n equal to 1. And helium with 2 electrons in the s subshell. You see, helium has only 2 electrons. And both those electrons are in the main energy level n equal to 1. Because n equal to 1 has a subshell s that can hold 2 electrons. So what is the configuration for helium? Can you write that for me? It will be 1s2, 2 electrons in the s subshell of n equal to 1. 1s2. 2 electrons in the s subshell of n equal to 1. Now look at carbon. Carbon has 6 electrons. How are they going to be distributed? Remember, n equal to 1 can hold only 2 electrons. Alright, so carbon with 6 electrons has 2 electrons in n equal to 1, and the remaining 4 will go to n equal to 2. And how are they going to be distributed? It will be distributed, 2 of them will be in the s subshell and 2 of them will be in the p subshell, because s subshell can only hold 2 electrons. So how will we write the configuration? What's the configuration for carbon? The first 2 electrons are the 2 electrons in the s subshell of n equal to 1. That means n equal to 1 is now full. It can only hold 2 electrons. Now we go to the n equal to 2. n equal to 2. 2 electrons in the s subshell of n equal to 2. And the remaining 2 electrons in the p subshells of n equal to 2. So the electron configuration for carbon is 1s2, 2s2, 2p6. Alright? Aluminum with 13 electrons. Alright. Can we work out together? Let me see if I can write on the whiteboard. How do we do this? You got to first of all divide them into n equal to 1 and n equal to 2. Remember, how many electrons can there be at n equal to 1? n equal to 1 can only contain 2 electrons. n equal to 2, what is the maximum number of electrons that n equal to 2 can contain? That's 8. So 8 plus 2, 10. There are 3 electrons left. That will go to n equal to 3. So that means these electrons are now going to be distributed to n equal to 1, n equal to 2, n equal to 3. Alright, let's write that down. Now, n equal to 1 can only contain a maximum of 2. n equal to 2 can contain a maximum of 8. And n equal to 3 can contain a maximum of 18. So, when you have aluminum with 13 electrons, you're going to put 2 electrons at n equal to 1, and which subshell that is going to be? N equal to 1 has only one subshell. That means these 2 electrons are going to be in the S subshell for n equal to 1. And look at the way I'm going to write it. I'm going to write it as 1s2. So both these electrons are in the S subshell for n equal to 1. Alright, we now go to the next n equal to 2, and there can be 8 electrons in there. And those 8 electrons we got to assign to S, P and D. Alright, how many electrons can there be in the S subshell? 2. And how many electrons can there be in the P subshell? There can be 6. So we're going to divide this 8 electrons, 2 electrons in the S subshell for n equal to 2, and the remaining 6 we will give it to P, and therefore that will be 2s2 2p6. Is that right? So these 8 electrons will be distributed as 2 electrons corresponding to n equal to 2 in the S subshell, 6 electrons, I don't know whether you can see it, I wrote it to the right of the screen, 6 electrons in the P subshell for n equal to 2. Well, how many are now left? Well, I can have 18 there, but I have only 3 that I need to. So I'm going to cut this 18 and I'll write 3. And this 3, the first 2 of these 3 are going to go to the S shell for n equal to 3. So I'm going to say that will be 3s2 and 3p1. Is it okay? I take 2 out of this and put it in the S subshell for n equal to 3, and the remaining 1 I gave it to the P. And so, what is the electron configuration for aluminum? Put it all together. It will give me 1s2, 2s2, 2p6, 3s2, 3p1. Look at that. That is the electron configuration for aluminum with atomic number 13. It tells you, let me read it out for you. It means the first 2 electrons in the S subshell for n equal to 1. The next 2 electrons in the S subshell for n equal to 2. The next 6 electrons in the P subshell for n equal to 2. That means I have now completed n equal to 1 and n equal to 2. I have to now go to n equal to 3. Of the 3 remaining electrons, 2 of them are in the S subshell for n equal to 3. And the last electron then will be in the P subshell for n equal to 3. Isn't that easy and interesting? Okay, I'm going to ask you to do one like this on your own. Alright, so electrons, aluminum with 13 electrons will be 1s2, 2s2, 2p6, 3s2, 3p1. Okay, now write down the configuration of the following elements. Sulfur of atomic number 16, argon of atomic number 18, calcium of atomic number 20. Alright, if you send that to me, that will be 3 extra credit points. Alright, I haven't given you extra credit points for quite some time. So if you want to do this, it's not mandatory, but if you want to do this, you can earn 3 extra credit points by sending me the electron configurations for these elements. Alright, let's move on. Well, That means the energy levels that we saw in the case of Bohr model. You remember the energy levels? I gave you the energy values and we calculated the energy of a photon. Well, when you bring it to the quantum model, it is going to be much more complicated. Why is it much more complicated? Because each energy level, E1, E2, E3, has now sub-levels. So that's going to make it very complicated. Look at these. Each n equal to 1 has one subshell. N equal to 2 has two subshells, 2s and 2p. N equal to 3 has 3s, 3p, 3d. So look at the complication. I don't want you to get giddy or get a headache by looking at this. Don't worry about that, but just understand that the quantum model of the atom is a lot more complicated. Now, it's a beautiful model. It explains the behavior of all the elements. You see, that's the beauty of it. The energy level diagram using the quantum model is a lot more complex than the one we saw in Bohr model. There are many more intermediate levels. In Bohr model, we only saw levels n equal to 1, n equal to 2, n equal to 3, and so on. But in the quantum model, there are many more intermediate levels. That means there are a lot more possibilities for electronic transfer. Now remember, white light is made up of 3,000 different wavelengths. That means 3,000 different photon energy values. So all these 3,000 energy photon values can be accounted for by using the quantum model. It describes it well. Isn't that a great achievement? I think so. Quantum mechanics actually predicted the behavior and it did very well, although it is based on probability. Now, whereas Bohr model could only explain hydrogen atom. Well, hydrogen atom is a simplest atom, only one electron. Bohr model could explain it very well. But when you go to higher elements, Bohr model could not explain it. It needed the quantum model for that.